It's a search for our beginnings. The massive planet Jupiter holds the key to understanding the formation of our solar system, our planet, and life itself. NASA's Juno mission is unlocking the mysteries of the gas giant. Principal investigator Scott Bolton joins us with the revelations from Juno's journey to the fifth planet from the sun. That's next on this episode of Technology Today. We live with technology, science, engineering, and the results of innovative research every day. Now, let's understand it better. You're listening to the Technology Today podcast presented by Southwest Research Institute. Hello and welcome to Technology Today. I'm Lisa Benya. NASA's Juno mission launched in 2011 and entered Jupiter's orbit in 2016 to explore the planet. The spacecraft continues orbiting the gas giant, recently beginning its extended mission. Jupiter represents the very earliest part of the solar system and is key to understanding the formation of all planets and life on Earth. Juno is unlocking the mysteries of Jupiter and rewriting the textbooks on the fifth planet from the sun. Our guest today is a theoretical and experimental space physicist. He's Associate Vice President of the SwRI Space Science and Engineering Division and Juno Principal Investigator, Dr. Scott Bolton. Thank you for being here, Scott.
Thanks for having me. It's great to be with you and your audience.
So the Juno mission is fascinating. The spacecraft launched 10 years ago. The data, the pictures are just incredible. You are heading up this mission. The primary mission has just ended, and you recently started the extended mission, which will go to 2025. We have so much to discuss today. So let's get started with the gas giant Jupiter. Why the focus on Jupiter? How did this planet become the centerpiece of the Juno mission?
So the reason Jupiter is so important is because it's the largest of all the planets. It's more massive than all the planets put together. In fact, they would all fit inside Jupiter, basically. And so when you're trying to understand sort of the recipe of how you make a solar system and how did we get here on the Earth and what happened in the early solar system, Jupiter's really the first stop. And it's because it must have formed first. If it had formed after the solar system was already created and the other planets, it almost certainly would have disrupted everything. So most scientists believe it must have formed first. So that's the first step in planetary formation. After the sun formed, then the first planet must have been Jupiter. And so when you want to kind of investigate and understand where we came from, how planets are made, how other solar systems are made, when we look out at exoplanets, planetary systems, we look and we basically compare it to Jupiter. And so Jupiter's really giving us the clues.
Juno launched in 2011 and jumped into Jupiter's orbit in 2016. You've been collecting data and images for 5 years now. What do you consider the most significant discoveries of Juno's primary mission?
So that's a long list, and I'll try to take them in the order that we realized them when they were happening. So the first thing is Juno is really the first spacecraft to go over the poles of Jupiter. So it gave us the very first view of what Jupiter's north and south pole looked like, and it didn't look like anything that anybody had expected. We had seen Saturn's pole, which had sort of a hexagonal shape of a line of atmospheric features, but it pretty much was pretty bland. When we got over the pole of Jupiter, there were giant polar cyclones. In fact, on both poles, and they were all shaped basically like a hurricane on the Earth. They were very circular in shape, like a vortex. But there were different numbers. There were 5 of them over one pole, surrounding a center one, sort of in the shape of a pentagon, evenly distributed, 5 of them. And on the other pole were 8 surrounding a central. So that was more like, and they were all evenly distributed, sort of spaced out, like they were sharing this space. And so that was a real surprise and in fact, scientists are still working on theoretical ideas of how to explain how those polar cyclones are created whether they're changing, how long do they live for, and they're gigantic. They're thousands of kilometers across. I mean, they're not quite as big as the Great Red Spot, but they're very significant storms. Then as we started to explore Jupiter more and more, we started looking at the deep atmosphere. So we have special instrumentation called the microwave radiometers, and they actually can see through the cloud top. So when we look at Jupiter, the way we're used to looking at it, we look at it from an equatorial perspective, but you look at it with Hubble telescope or some of the previous spacecraft, and you see Jupiter as a series of stripes. We call them zones and belts, and those are actually jet streams going back and forth. They're a little bit different color. Some are a little browner or redder than other ones, or whiter or more yellow, and that's probably driven by the chemistry, but they're actually winds that are moving back and forth in different directions and at different speeds. And then you have this giant Great Red Spot, just in the south of one area. And of course, that is the longest living storm that we know of. Well, when we started to look at Jupiter deep down with our microwave radiometers, we realized that those zones and belts are not just shallow features. They go pretty deep, 4,000 kilometers down into Jupiter. So these things are penetrating down. And then underneath that, Jupiter seems to be rotating around as a solid body. So that was a pretty major discovery. We're also, as we're looking at this deep atmosphere, we realized it wasn't well mixed. And that went against every theory that existed at the time. Scientists always thought that once you drop below basically where the sunlight shined, so if you had clouds that blocked it, the weather was driven by sunlight like it is on the Earth, and that once you got beneath that, or certainly beneath where water condenses and the water clouds were formed, that everything would be well mixed and stirred up inside. But in fact, it isn't. We look down as deep as we can see, and we see that ammonia and water and other pockets are all highly variable, not only as a function of latitude, which is very puzzling, but it also has time variability in it. It's changing. So things are happening. The weather layer on Jupiter goes much deeper than where the sun can reach, or where water condenses, which is largely believed to be the driver of weather. So we're still trying to figure out exactly how that works. One theory that we've seen evidence of is that there may be sort of mush balls, which is sort of a mushy like hail that's being formed in Jupiter's storms and dragging down ammonia and water down very, very deep, like hail does on the Earth. Here in Texas, we get hail, and you often can see the hail landing on the ground on your driveway or on your street, or if you're unfortunate, on your car. And of course, the hail's ice, and yet it's warmer than when ice melts, and yet the hail's still there. So like at Earth, or like our hailstorms, Jupiter has some kind of, but they're giant hail, and they're mushy, mixed with ammonia and water probably. And so this was a pretty major discovery, and just the whole idea that Jupiter's deep atmosphere is highly variable. Another big discovery was we were searching for its core. And we wanted to know whether Jupiter had a small compact core or none at all. And that was going to help us constrain how Jupiter formed. Did rocks sort of collect first in the early solar system, and then when enough gravity was formed from the rocks, it sucked the rest of the gaseous atmosphere, which is mostly what Jupiter is made out of? Or did it form more like we think a star forms, where this cloud, just all of a sudden an instability gets created and the cloud forms a star with no central core? And we were surprised again, because neither answer that we had set out to try to discover, which was a small compact core or no compact core, turned out to be true. Instead, Jupiter has a very large core without hard boundaries. It's not compact, and it's sort of a fuzzy core. We call it a dilute core. And it doesn't fit any of the theories of how Jupiter formed or evolved. And so those theories are kind of going back to square one and saying, how do you make giant planets? What happened in the early solar system that formed Jupiter? One idea is maybe it suffered from a very giant impact early on in its life, but we're still looking for evidence of whether that might be true. Models don't quite make that work. Another discovery had to do with its magnetic field. We saw features in the magnetic field that were being distorted by the jet streams, the winds deep in Jupiter, which meant this was another piece of evidence that the jet streams and the winds in Jupiter were actually going quite deep. They were going deep enough so where the atmosphere was ionized or charged from pressure and temperature, and the magnetic field was charging this atmosphere, and so the winds were actually twisting the magnetic field around a little bit, and so that was a big surprise, and it really taught us that the atmosphere and the interior are very much in communication with each other and are affecting each other. And that sort of opens up a whole new field. Prior to Juno, scientists from these different fields often worked alone and in isolation, not thinking that one thing was actually affecting the other. But on the Juno team, we've started to become much more interdisciplinary, where we realize the atmosphere, the interior, and the magnetic field, and even the magnetosphere are all coupling to each other and affecting each other's scientific outcomes.
So, I mean, it's just a huge list of discoveries over 5 years. It's expected, there's just so much data, so many images pouring in. What does it feel like to be on that team, watching this in real time come in and just realizing that, you mentioned being surprised quite a few times there. So what does it feel like to be on a team making these huge discoveries? And as we mentioned earlier, rewriting the textbooks on Jupiter?
Well, I think we all feel really fortunate and honored to be part of something that's, sort of revolutionary in our revolutionizing our understanding of the solar system and the cosmos. Um, I think it's also a very humbling experience. You set out to achieve certain science objectives, and you lay out what you expect and what your certain questions you're hoping to answer. And usually you're lucky, or you stumble into maybe one or two things where, your ideas are shown to be wrong, and the science community has to kind of go back to square one. I think that it's the first time for most of us where we're having that happen so often, and it's across the board of all of our scientific disciplines. I mean, I only touched on a few, but people that study the magnetosphere, people that study the magnetic field, the interior, the atmosphere, planet formation, atmospheric dynamics, all of those are sort of, it's a very humbling experience to realize everything you've been spending your time and reading about in books needs to be rewritten. And so it's a lesson, but it's also incredibly exciting and a privilege to be part of something that's so revolutionary.
How did you propel the spacecraft into orbit around this massive planet? How do you achieve that?
So initially, you start off with a rocket that launches you from the Earth, and that rocket has a number of stages to it, and your spacecraft is tucked away inside at the top. And as the stages happen, first you get into Earth orbit, and then another rocket fires you into the direction that that trajectory engineers, which are orbital dynamicists, and they're an amazing field by itself, have actually calculated and realized how you literally drive to Jupiter, right? It's really amazing to me that we understand how to navigate the planets in our solar system. I'm in awe of the engineers that calculate that. They're using Kepler's laws and basic physics, but it's amazing that it all works and they can do these fine tunings. So you get launched into a direction that is all calculated ahead of time, and you actually we didn't have enough energy to get there. We're not the first that have used this trick. We use a gravity assist. So we go around the sun, and while we go around the sun, we reach out to maybe near the orbit of Mars or the asteroid belt, and then come back to the Earth, and the Earth kind of gives us an extra boost, like a slingshot, and then you get going even faster relative to the sun. And so then your orbit moves out even further than Mars or Jupiter, because you've gotten almost like another rocket boost from the Earth. You're literally getting close to the Earth, and Earth slows down slightly and transfers some angular momentum to the spacecraft. And that lets you reach out to Jupiter's orbit. Now, the next trick is, once you're at an orbit that's going to reach to the distance that Jupiter is from the sun, everything has to be timed. So when you reach that distance, you're actually next to Jupiter. So that's all calculated ahead of time. And then when you get to that place where you're going to be close to Jupiter, you fire another rocket that you're carrying on board, a main engine, and that essentially slows you down. Because if you don't fire that rocket, you're just going to fly right past Jupiter. And so you slow down, and then Jupiter's gravity field grabs you, and then you're in orbit around Jupiter. And so that's the whole trick. And it's it's a very nail-biting experience, because if that rocket motor, when you're just at Jupiter, doesn't fire at just the right time for the right duration and in the exact right direction, then you lose the entire mission. You don't go into orbit at Jupiter, or something could happen where you just explode, and that's the end of the mission. So it's a very tense moment, just like the launch is. If the rocket goes wrong at the launch pad, you'll lose everything. But at Jupiter, you've already spent so many years waiting to get there. The anticipation is there, mixed with the tension. But it's also very exciting, living on the edge.
Yeah, so carefully orchestrated. When you were saying, they know the route around our planet and to get you there, all I could think of was, this is so way beyond like punching in your destination in Google Maps. This is like next level, just having a complete knowledge of everything they're going to encounter along the way. So just fascinating. So Juno orbited Jupiter 34 times. Why this precise number, and what did each orbit accomplish?
So we were basically designed to map out the planet. For our science objectives, we wanted to be able to understand the gravity field of Jupiter, the magnetic field of Jupiter, and the atmosphere, and look at the magnetosphere. And to do that, you'd like to map out the planet, map out the environment around it. It's sort of like if you wanted to map out the Earth, if you only went over Texas, or went over Texas and then Hawaii, you wouldn't get a very good feel for how everything varied. You have to go over every place, sort of every so many degrees longitude. And so that's what the mapping was. Each orbit was designed to go over a specific longitude of Jupiter, close in. Our orbit is elliptical, and so one part of it, we go very, very close to Jupiter, only 5,000 kilometers above the cloud tops. And so that's designed so that it goes over a certain longitude. And then the next one goes over a longitude maybe 180 degrees away from that. And then each one is spaced out. And so what we did was we made a map that was 16 orbits around Jupiter. And of course, it's 360 degrees around. So you can do the math and see that we've spaced it out. And then the next set of orbits went in between those longitudes. And so by the time you had 32 orbits, you had basically got a complete map of Jupiter, that was evenly spaced in longitude. And then we had 2 spare orbits, just in case something went wrong, we could make up one of those longitude or pieces of the map. We didn't want any gaps in the map. And during the time, we did have one orbit where the spacecraft went into a safe mode, and so we didn't get data. And so we needed basically 33 to complete our map of 32 orbits. And then we still had the one spare. And you talk about how everything has to be so carefully planned out for the navigation, and it does. It's really amazing. but the navigation is done in some ways the same way we've done for centuries. So ships, when they were discovering America and things like that, would look at the stars to navigate with. And that's exactly how spacecraft work, is they have cameras, special cameras that are low light cameras that look up and look at the stars, and they make a map of the stars and then compare it to a map that's in their computer inside the spacecraft. And of course, we have them on the Earth as well for the operation engineers. And we compare, and that's how the spacecraft knows where it is. It takes pictures of the stars. So we're literally navigating by starlight.
I love thinking about that. As you said, when the explorers were discovering new lands using the same method, stars. Amazing. So, we hear a lot about Jupiter's moons. Jupiter has 79 known moons, 53 named, 26 awaiting official names. Io, Ganymede, Europa, and Callisto are the planet's four largest moons, known as the Galilean satellites. What has Juno revealed about Jupiter's moons?
So, it wasn't in our original plan, but since we're, of course, orbiting Jupiter, and because we had a polar orbit, we were going above and below the moons. And nobody had seen that before, because previous NASA spacecraft had always stayed near the equator and could only look, just like at Jupiter, you would look at a side shot, basically the same view you'd get from the Earth. So when we went over the poles, we took the cameras and pointed them at these satellites. We managed to get pictures of Ganymede and Io from above. And on Io, which is the most volcanic body in the entire solar system, we saw what the volcanoes look like at the poles of Io for the first time. We also made maps of Ganymede. You have couple of missions that are actually following Juno that are going to be launched soon, and they're going to explore those two bodies. One by the European Space Agency named JUICE is going to explore Ganymede, and NASA's own Europa Clipper mission is going to also be launched in a few years and be exploring Europa. So we got the first view of what those moons look like from the poles, and in our extended mission, we actually are going to get really close to those moons. So we already, over this last summer, flew by Ganymede very close, just about 1,000 kilometers or so above Ganymede's surface. And we got incredible images. And we compare that also to more distant shots where we're seeing the poles, and we learn about the composition, the ice shell, how Ganymede has its own magnetic field. So we explore that a little bit. We do a radial occultation to understand its atmosphere. And we look at the whole interaction of Ganymede, the moon, with the magnetosphere. Each of these moons of Jupiter affect Jupiter's magnetosphere and actually show up when you look at Jupiter's aurora. Because there's like an umbilical cord moving along the magnetic field that comes out of Jupiter that threads through these Galilean satellites. And so you can see a little footprint lit up, and you can see Ganymede's footprint, Europa, and Io. And in fact, Io, because of its volcanoes, creates a footprint that goes, a fair fraction of a way around Jupiter because of all the volcanic debris that sort of trails behind Io, also creates aurora for us. So in our extended mission, still coming up sometime next year, we'll go by really close to Europa, only about 350 kilometers away from its surface. So we'll see new things with Europa that we're very excited about. And then we have two flybys of Io that are 1,500 kilometers, and that'll tell us about its interior, whether the magma ocean is global or just in little pockets. These moons have oceans. The Ganymede has an ocean underneath its ice, and Europa certainly has an ocean underneath its ice. And so we're going to be exploring how those oceans work. Maybe are there pieces of them that are closer to the surface, and what is the ice shell around these? We have some special instruments that the future missions don't have. In particular, one of them is this microwave radiometer, which we use to look, and it was designed to actually look deep into Jupiter's atmosphere. When we point that at Ganymede or Europa's ice shell, or even Io's, we'll make a map of that ice that tells us something about how its composition and structural properties change across the moon's globe. And it may tell us where parts of the ice are shallow or in communication with the ocean underneath. It's going to tell us a lot, and we don't have that data even on these future missions. We don't have anything exactly like that. So we're working with those teams to help complement them and get them more prepared for their own investigation. And of course, once they get their data, we'll go back and we'll use Juno data at these moons to try to make a bigger picture, tell us more about the moons themselves.
So, one other well known feature of the planet is the giant red spot. What have you learned about this giant storm?
So, the giant red spot is a great example of something that's very well known, but reasonably poorly understood. And we know that it's lasted a long time. And we're lucky to have Juno there right now studying it because it's going through a period of change. We see it appears to be shrinking. There's some debate whether the storm itself is getting smaller or if the top layer is getting covered by other clouds and it just appears to be smaller. And so we're studying that, watching those changes, and certainly learning about the dynamics of the Great Red Spot. But there's two pieces of things that we really looked that are of particular interest to us. And that is, one, with the microwave radiometer, we can actually look underneath the layers of the Great Red Spot and see how deep it goes. And it looks like it goes pretty deep, but we're still looking at the details of that and modeling it. But it's going to kind of provide us new information and new models of how the Great Red Spot works. That's one thing that Juno is working on and doing. Another is we have other techniques that we can look at how the Great Red Spot affects Jupiter's gravity field or magnetic field. And so that tells us also something about it, its depth and how it's structured and how much mass is tied to that storm. Are there other storms like that? And so we're kind of learning about the Great Red Spot, which is sort of the chief storm there at Jupiter, but also comparing it to the other types of storms and vortices that we see all across. I mean, one of the amazing discoveries of Juno is how incredibly beautiful Jupiter is. That when you really get up close and you get these camera shots, you see it's like a palette, like a Van Gogh painting. And these storms are swirling around in different colors. And it's very unique in the solar system in that it's such a natural beauty. We have a website where we put this data up for anybody to process. And the citizen scientists go on and make the pictures. But I would say there's almost an equal number of artists just inspired, and they're making art pictures out of Juno's images of Jupiter. And so, and the Great Red Spot is right in the middle of that because it's an incredibly beautiful storm. We even see little clouds at the very tops of it that we think must be where the precipitation or ammonia ice must be forming. And that's something that Juno found all over Jupiter, that there's these high level clouds. We can almost see clouds at different levels, and some of them must be made of ice, and other ones are made of liquid or gas or a mixture.
Yeah, so since you mentioned it, let's talk about the pioneering citizen science campaign that your team created. So, Juno is the first NASA mission to have a dedicated camera for the public. And as you said, citizen scientists take the Juno Cam images and upgrade them, adding color and highlighting the planet's beauty, as you said, the unique features. So, the campaign also invites input from amateur astronomers. How does this open platform enhance the Juno mission?
So first, the citizen scientists that work with the images that we take, they're not just changing the color, they're actually producing the image itself, just like scientists would. We load up the raw data, which doesn't look anything like an image. It's digital, and we're spinning, and so the image data itself has to be, played with on the computer and organized and and then you make an image, and then you colorize it. And we have 4 different filters, and so they get to choose that, and that helps in scientifically as well as artistically. And then we have this big program for amateur astronomers to look at Jupiter at the same time that we're flying by. And we publish when we're going to fly by it and which longitudes we're going to see. And they train not even professional astronomers using Hubble telescope and special facilities all across the Earth with infrared and different wavelengths will look. But then the amateurs also help us because they get more coverage than the professional ones. There's only a few big telescopes that can be trained on Jupiter at any given time. And so the amateurs fill in the blank and give us more constant coverage. And so one of the direct links is when we see something strange or new in the radio or in the microwave or even in our image, we get the context from the amateur community because they get the picture and they watch how Jupiter's atmosphere is evolving. Sometimes they warn us about stuff and they say, hey, a big change has occurred here. We had something that happened not too long ago that was called Clyde Spot, where an amateur named Clyde in South Africa was taking an image of Jupiter and saw a big white storm forming just south and a little bit to the right or east of the Great Red Spot. And so he put out an alert. And it turned out the next day we were flying right over that. And so we got a close-up picture of Clyde's Spot. And then and we've watched this evolve. This was a giant storm that formed very quickly, and then we've watched it evolve. And so the amateur community, as well as the professional community, are playing a big role in connecting to us and expanding our science that we can do. Sometimes with the citizen scientists, we actually they're doing such important stuff, we invite them into our own publications. And they become part of the team, literally.
I mean, how exciting for them and how exciting for Clyde. So all the amateur astronomers out there can shoot for the stars, so to speak, and can aim to become Clydes and put their information out there. And I just want to put the website out also. You can see the citizen scientists' work at missionjuno.swri.edu/JunoCam. Of course, we'll have this web address on our episode 35 page. Really cool work. So right now, I want to play a unique chorus of sounds for our listeners, sounds created with Juno data. So let's hear it. Interesting sounds we just heard. Will you explain what we just heard?
Sure. So you're actually listening to a radio. So we fly a radio. We have a plasma wave and radio experiment on Juno, which is literally an antenna, like the old kind of antennas that used to be on TVs, just a couple of wires. And it measures radio emission that's coming from Jupiter's magnetosphere generally. And this one was connected to the aurora. And so what we're doing is we're getting radio emission that is at a certain frequency. And the human ear can hear sound frequencies that are usually about speakers or maybe go from 20 to 20,000 hertz in frequency. And so these radio emissions are basically converted down through a mathematical routine to get them to within the right frequency that you could hear with the human ear. And then you're literally playing it. Now, it's not exactly sound, because in order for a sound wave to work, you have to have air. And there's no air out there in space. It's a vacuum. Of course, there's air inside Jupiter's atmosphere, but this is outside outside the atmosphere and the magnetosphere. So there's no air out there, but you do get radio. And in the same way that the radio works in your car or at home, it's coming in at a certain frequency, and then the radio electronics converts that into a sound that you can hear and plays through your speakers. And so they're changing the frequencies. Ours are doing the same thing. We're basically taking the radio. So this is what you would hear if you flew a radio at Jupiter. And literally, that's what we're doing. And so we're actually listening to the sounds that Jupiter's magnetosphere makes, but they're really radio frequencies that are converted into sound waves.
So the sounds of Jupiter are now incorporated in songs. You have worked with a long list of artists. Where can we find this music? Who are these artists?
So there's a wide array of artists that have incorporated these sounds, everything from country music to jazz to hip hop to rock and roll to new age music. And some of them were collected by Apple Music and put out on a special website dedicated to Juno. And you can look up, an Apple Music, Jupiter and Juno, and you'll find a large collection of sounds. Others you can find where they, were published by the artists themselves. So in the country arena, Brad Paisley did a song that incorporated these sounds called Sister. And then Little Big Town, I worked with them where it was a tribute to Elton John's Rocket Man. And we put together a great version of Rocket Man that was largely driven by the percussion, which was really the beat and rhythm that was driven by Juno sounds that I put into the mix and they worked with. And then Vangelis, the composer who did Chariots of Fire and Blade Runner and a bunch of other movies, he's worked on a number of pieces of music using the sounds themselves. So did Trent Reznor from Nine Inch Nails. I did a video with him that Apple also produced that was on the mixture of art and science and how Juno works. And the score to it was put together by Trent, and he incorporated these sounds that you're listening to. The hip hop band Wu-Tang Clan, one of their artists that is a member of the band named GZA, is a very close friend of mine and works with science and loves science and lectures on it. He also used these sounds, and the list goes on and on. Herbie Hancock. I mean, there's just all kinds of different musicians that have incorporated these sounds.
Yeah, so the sounds of Jupiter are versatile and can be used in so many different kinds of music. I think that's really neat, and I encourage our listeners to go out there and search for these tunes and listen to Jupiter incorporated in music. Listen to the sounds of Jupiter incorporated in music. How cool is that? So I want to talk about your team and about the instrumentation you use. All of these findings are possible because of your talented team working with the tremendous instrumentation aboard the spacecraft. The solar-powered spacecraft itself is an engineering wonder designed to hold up to Jupiter's hostile environment. Tell us about the spacecraft. You mentioned the microwave radiometer quite a bit, but tell us more about these instruments and also its special radiation vault.
So we have a lot of science instruments as part of the payload on Juno. We have a visible light camera, which we call Juno Cam, and that's of course the one dedicated to the public. And then we have an ultraviolet spectrometer or spectrograph and an imager that was made by Southwest Research Institute. We have an infrared imager and spectrometer that was made by the Italian Space Agency and contributed to NASA as part of the mission. Then you have an array of fields and particles instruments. Very important to that is the magnetometer, which maps out the magnetic field that was made by Goddard Space Flight Center. And there's actually two magnetometers, one they're sitting on the end of a solar array, one of the solar array booms, and there's one outside, one on the inside, so that you can understand and remove the magnetic field that the spacecraft has and only measure Jupiter. And that's co-located with 4 visible light cameras made by the Danish Technical University. in order to locate exactly if the solar array were to bend a little bit, we want to know exactly where that magnetometer is. And so these are special cameras. They're actually star cameras that look out and look at the stars and figure out exactly where the magnetic sensors are in space. And then we have an array of instruments to study the aurora. We have a plasma instrument made by Southwest Research Institute, energetic particle instrument made by Applied Physics Lab, and the plasma wave and radio emission that we make the sounds from is out of University of Iowa. And then we have the gravity field, which is radio science. And so we use sort of the communication system, and that's a dual frequency. One part of it is the high gain antenna, which is used for communications, is made at JPL, and we call that X band. And then we have something contributed by the Italian Space Agency that is the Ka band, so another frequency. You use both of those frequencies so you can remove the noise. And in fact, we're the first spacecraft to use dual frequency. Cassini launched with two of them, but one of them failed. So we're the first ones to really have one that works in both frequencies. And it helps you get the radio science even more precise, which of course is what we're using to understand Jupiter's core. And then finally, we have a new kind of instrument that was literally invented for Juno, and it's called the microwave radiometer. And it's actually 6 instruments hiding as one. There's 6 separate antennas and receivers that are looking at radio wavelengths between 1 and 50 centimeters. And so each wavelength sees into Jupiter at a different depth. It's almost like radar, but it's passive. There's no bounce. It's not broadcasting a signal. It's just listening to Jupiter. And if it's a long wavelength, it's listening from deeper down. And if it's a short wavelength, it's looking sort of at the top part of the atmosphere. And that instrument was built at JPL. And that is, there's a lot of interest in that instrument because it was brand new. Nobody had ever used anything like that on a planetary mission. And it's so revolutionary that my guess is that it'll be used to study the other giant planets in the future.
So the Juno team has started the extended mission. Where is Juno right now? What can we expect during this extended mission? And what happens to the Juno spacecraft in 2025 once the extended mission is over?
So the extended mission started August 1st. And what's happening is even though we have some fuel on board and some, little rocket motor, so to speak, we're no match for Jupiter's immense gravity field. And so as we get so close that Jupiter pulls us around and twists our orbit, and so it keeps twisting it sort of so that the place that we crossed Jupiter started off near the equator, and it's slowly moving more and more northward. And it's because Jupiter's literally twisting our orbit around. And what that does is it has a benefit to us in the extended mission, because it means that orbit being twisted around allows us to go very close to the satellites, and it allows us to explore Jupiter's rings really close. And we get close-ups of the northern hemisphere and the North Pole, and more than we did during the primary mission. And all of those are science objectives that are highlighted in our extended mission, some of them brand new, like the study of the satellites or the ring system. The ring system of Jupiter is virtually unexplored. And of course, a lot of the puzzles and discoveries we made were in the northern hemisphere. And so we're going to get up close and understand, what happens in Jupiter's atmosphere where the atmosphere changes from these stripes, the zones and belts, to somehow forming the polar cyclones. And also, we'll get more gravity and magnetic field data. We'll study this interaction of the deep atmosphere and the magnetic field in the interior, and constrain the core more and more. So that's what's coming up in the extended mission. Now, at the end, we've postulated that we have enough fuel to get all the way to the end, and maybe even have a little bit more. And the solar arrays, which were the first solar-powered mission to reach Jupiter's distance, they will slowly degrade from radiation, but it looks as if they're doing pretty well right now. They have special cover glass on them that protects them from the radiation, and they're pumping out energy that is more than we need at the moment. And so there's a little bit of cushion there or margin as the solar arrays start to produce less. The thing that's probably most dangerous for us is Jupiter's radiation. And as this orbit twists around, we go through more and more harsh radiation, regions of harsh radiation. It gets harsher and harsher. Each time we go by, we get another dose of radiation, and even stronger dose each orbit practically. And eventually the radiation will penetrate into our electronics and probably cause failures, maybe slowly, but eventually that may kill Juno. And you mentioned the radiation vault. We were the first ones to design something like that because we had to. We were the first, mission that was actually looking at trying to go into, the harshest radiation environment in the entire solar system. And so we took a very novel approach and we built a vault made out of titanium. So we, in the middle of the spacecraft, we have basically walls of titanium, and their mass is like 200 kilograms altogether. And then inside that vault are all the sensitive electronics. And even with all that shielding, some radiation is going to get through. I mean, that it was designed to protect us to last through the prime mission with some margin. And of course, we passed that prime mission mark on July 31st of this summer, 2021. And we see no real negative effects. So we're built like an armored tank, and the shields are still holding. And so that's very positive. But someday those shields are going to fail, just like on Star Trek.
Okay, so Juno has done its job. It continues to do its job, built like an armored tank, but one day it is going to succumb to the forces of Jupiter. And, it's kind of sad, to think about that, but it's provided so much data and good information that, so gotta think of the good times, right, with Juno?
Well, and you couldn't learn what we wanted to learn about Jupiter and our early solar system without going in really close. And so that was really the novel approach and concept of Juno, was figure out a way to get at data that NASA couldn't get up till now.
So I wanted to touch on the Lucy mission just a bit. A new Southwest Research Institute-led mission is set for launch in October. That's the Lucy mission. It will begin a 4 billion-mile journey to explore Jupiter's Trojan asteroids. And what an elite club you are in, overseeing a space mission. I know part of your job here at the Institute is to bring new missions to fruition. Did you have any collaboration with Lucy and the Lucy team, and any words of wisdom for this team as they begin their journey?
So early on, I did work with the Lucy team and help put together, some of the structure and partnerships that went into really developing and building and implementing Lucy. Southwest Research Institute, of course, is the leader of it, and I worked with the leaders on Lucy to put together that, and then combine them with Lockheed Martin, who ended up building the spacecraft, and also Goddard Space Flight Center, which is a NASA center, to help manage the mission and oversee it. And that went into basically the whole proposal architecture and how how Lucy would be implemented and designed. And so I was very happy that they took the reins and ran with them, and were able to put together such an incredible concept, and all the great engineering and design that they put together to win that mission and actually successfully build it on cost and on schedule, which is a big challenge. And so no doubt all of their partnerships under Southwest Research Institute's leadership was able to pull that together and have a great success story. Now they're approaching launch, and it's a very tense moment. It's also a very exciting moment. It's probably one of the most exciting times of the entire mission, but also one of the most tense. And so my advice to them is, enjoy that moment and try to, make sure that you don't let the tenseness of the fact that the launch is so high risk get in the way of enjoying the moment. and be careful, and of course, but really enjoy the fact that you're finally launching and getting on your way. And then comes this long trajectory to get out to where you're going, and you have to be patient. And in the space program, patience is a virtue. You watch entire generation or your kids grow up while you're waiting to get out to your target. They're going out to a very far target, the Trojans around Jupiter, which are asteroids that are orbiting near Jupiter's orbit. So it takes a long time to get out there. And in the meantime, the excitement will just continue to build. And then when you arrive, another really exciting time. They don't have to get into orbit like we did with a Jupiter orbit insertion, but it's going to be a really exciting time. And be prepared for the ideas that you had at the time you formulated the mission to actually change. And that data you're going to get is going to change your theories and change your concepts of how the universe works, how the solar system works. And that's part of the incredible excitement. So I wish them all great luck and fortune, and I hope they really enjoy the journey that they're about to embark upon.
Enjoy the mission, be patient, and get ready for changes in your plan. Great advice. What do you hope our listeners take away today? What is Jupiter teaching us about planetary science, about life?
Well, it's teaching us about our origin and where we came from, and how pieces of the puzzle come together to tell a bigger story. And that's a very important lesson for all of our listeners to get is that, you try not to answer every question at once. You have to be patient. And science works by gathering data and making progress, sometimes seemingly too slow. You have to be patient to realize that you're getting a piece of the puzzle, and that's got to go into that next bigger puzzle or help you with a theory. But also reach out and never really give up. If you've got something that you believe in, keep working at it, work with others, complement your expertise. If you're great at one kind of physics, you got to mix with the other kinds of scientists. You got to mix with people of all fields. Try to be creative, innovative, mix with artists, mix with people that think differently than you, and you can accomplish great things. And never lose sight of the big picture, because that's also really important to realize that your ideas and your perspectives can change. And while it's natural for us to resist those, it's also important for us to welcome those new revelations, because that's what, in the end, leads to innovation and a greater understanding.
Yeah, just wonderful advice for life in general. And, you've been a standout example of all of it throughout the Juno mission. What an amazing discussion today, Scott. Thank you for spending time with us and giving us this fascinating insight on Jupiter and Juno. And before we go, I want to say congratulations on your recent Space Pioneer Award from the National Space Society, recognizing your accomplishments on Juno and your work to open the space frontier, one of many awards you have received for your work. It's been a joy speaking with you today.
Thank you so much for having me and sharing the excitement of the space program with your listeners.
And thank you to our listeners for learning along with us today. You can hear all of our Technology Today episodes and see photos and complete transcripts at podcast.swri.org. Remember to share our podcast and subscribe on your favorite podcast platform. Want to see what else we're up to? Connect with Southwest Research Institute on Facebook, Instagram, Twitter, LinkedIn, and YouTube. Check out the Technology Today magazine at technologytoday.swri.org. And now is a great time to become an SwRI problem solver. Visit our career page at swri.jobs. Ian McKinney and Brian Ortiz are the podcast audio engineers and editors. I am producer and host, Lisa Pena. Thanks for listening.